In this video, I'm going to show you how to take the derivative of a function. It's real simple, but first we must understand what exactly is a derivative. So, we'll approach this the same way it was approached historically by Isaac Newton when he first discovered the derivative. He used it in terms of physics, and so we will use the same physics thought experiment. Let's say I have a ball, and when I throw this ball into the air, there's only one force that acts upon it, and that's gravity. So this is a constant force. We'll assume air resistance doesn't exist, and let's see if we plot this ball's position over time, we'll get something that's roughly parabolic like this. Now this is great and all, but what if we wanted to know the speed of a ball at a particular instance? Say if we wanted to calculate gravity, for example. Well, there's a big problem here. The speed of the ball, which as you know is given by the slope of the function, is constantly changing at every single point, because gravity is constantly causing the ball to accelerate or decelerate. And so what do we do if we want to find, say, the exact speed right here at t equals 2 seconds, right? Well, in the olden days, what we could have done is we could take like a stopwatch and we could have timed the ball, say from 1 second to 3 seconds, and then average the total time to get a rough estimate of the change in distance and get the speed like that. However, that information is not very useful when you have a very rapidly moving object. See, something like that's crazy. And so what do we do here? We need the derivative. And so the derivative is defined as the instantaneous slope of a function at a given point, or in other words, the tangent line of a function. So what exactly does that mean? So at some particular instant, let's say we use our same averaging example, there's going to be a change in position over time, or a change in x over t. Let's use this, right? And so we could draw a line between these 2 points and get the average speed of the object, whatever it may be, for this time interval here. And this is known as a secant line. But if we want to get a better estimate, we should start moving these points closer together, somewhere close to this point. And as you know, the slope of a function is equal to delta y over delta x. So if we moved it to here, we get a better estimate here, 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 and then ultimately so very, very close we're infinitely small. And so what do you do when you hear the term infinite? You use limits. And so we can define a derivative like this. We can essentially take the limit of the slope as delta x approaches 0. And so what does that look like? It looks like this. F of x plus delta x, that's our further point here, minus f of x over delta x. And so we can evaluate the change in a function using this limit definition. So let's say this function, which is parabolic in classical physics, is going by x squared, even though it's upside down. So we can say the limit as delta x approaches 0, f of x plus delta x squared minus x squared, all over delta x, which is delta x. So we'll say f of x equals x squared for your reference. And so let's solve this out. So then we have the limit. Don't forget to write limit every time or you'll lose points on the AP test of foiling this out. X squared plus 2x delta x plus delta x squared minus x squared all over delta x. And so if we cancel things out here, we can get the limit of delta x goes to 0 of delta x times 2x plus delta x all over delta x. These two cancel out, and so our final limit is going to be delta x approaches 0 of 2x plus delta x. Since this goes to 0, we just have the limit, or the derivative, of x squared becomes 2x. And so we can do this essential step over and over for every single function, but as you know, that takes way too much time, and we much prefer a faster way to do this in math, since we have to rely on derivatives so often. And so that brings us to our very first rule. And so you'll notice a bit of a pattern emerging here. So we'll make a column here. We have f of x, and we have f prime x, which is the same thing as saying dy over dx, or y prime. These are all ways of saying the derivative. So if we have x squared, as we found out, we get 2x. If we have x cubed, we get 3x squared. If If we have x to the fourth, we have 4x cubed. And this goes on and on and on. So what's the pattern here? You should probably be able to see right what we call the power rule. And so what is the power rule? The power rule basically states that the derivative of a polynomial like x raised to the n power is equal to n times x to the n minus 1. And this is a very important basic rule that you should definitely know. But what if we try to take the derivative of 2x, right? What is the derivative of 2x? Well, using the same process, 2x can be written as 2x to the first, so we'll bring the 1 down, and that becomes 2x, 1 minus 1 equals 0, x to anything raised to the 0 power is 1, so this is 2. And so therefore we have 2. And what about the derivative of 2? Well, 2 we can simply see is the same thing as 2 times x to the 0 power. Bring the 0 down, you already know we're going to have 0. And so this is our next rule. For any constant, the derivative is always 0. Also, when we're taking multiple derivatives, we can say, for example, if we want the second derivative can be written with 2 of those little dashes there. And that's essentially the same thing as taking the derivative of the derivative. So this is 2. We can also write this as d squared y d squared x, which is basically saying the derivative of y with respect to x twice over, or in other terms, y double prime. Let's say we have 3x cubed, right? Let's find the derivative of that. Well, if we bring down the 3 here, we have 3 times 3, which is 9x squared. And so the key here, which I want to point out, it's the same thing with 2x, is that when we have a constant, we leave it alone. It doesn't affect the derivative. It simply acts as a way to multiply to the function that is being derivatized. All right, our next rule, we'll get a little bit more complex. Let's say y is equal to 2x squared plus 7. Now we have two unlike terms. Well, what do? Well, in the case of addition or subtraction for that matter, we have a new rule. And that rule essentially is when we have two different things, we can just simply take the derivative of one and add the other. So we just treat these like they're separate terms. So if we do the math real quick, that's 4x plus 0, or 4x. Okay, another function. This one's even more challenging. Let's say we have y equals x plus 2 times x plus 3. Now we could simplify this by foiling and redistributing, but that can be a lot of work, especially when the function isn't this easy. And so what we can do is use the product rule, which is a way we can find the derivative of two things being multiplied to each other. So the product rule states that the derivative of f of x times g of x is equal to the derivative of f of x times g of x plus the derivative of g of x times f of x. And so what does that look for this function? What does that look like in practice for this function? Let's see. So the derivative of the first function, x plus 2, is going to be 1. So that leaves us with x plus 3. And the derivative of this function is going to also be 1 because I picked a really easy function for you to see. And so we're going to get x plus 2. And therefore this simplifies to 2x plus 5. Alright, now of course, since we did multiplication, the next logical step is to do division. So let's say we have x plus 2 over x plus 3. The quotient rule, I apologize for my bad handwriting, d dx, which is the same thing as saying dy dx, by the way. I don't know if I mentioned that. G of x. I know it can get a little annoying seeing all these different ways of saying the same thing, but you know that tends to happen with communication. This function is going to be the derivative of the top times the bottom minus, that's the key, the derivative of the bottom times the top. So it's sort of similar like this, but not quite, because then all of this is going over the bottom squared. And so the way people remember this is low d high minus high d low over the low squared. It's like a little sing-song you can do in your head. And so applying this to our function here, actually we'll make it a little more complex so you can actually see things happening. 2x plus 2 over 3x plus 3. How about that? So the derivative of the top is going to be 2 times the bottom, 3x plus 3, minus the derivative of the bottom, which is 3, times the top, 2x plus 2, all over the bottom squared, which is 3x plus 3 squared. And so we can simplify all this out. That's basic algebra. You know how to do this. we won't waste time. This one may seem a bit random, but it's important that we do it because it actually shows an unbelievable amount given how specific it is. Let's say we have the function y equals e to the x, which is, of course, the natural exponentiation equation, which looks a bit like that. And so the derivative of this, which may seem a little unintuitive, but I'll explain, is actually just the same function, e to the x. Why that is for this function and this function, really only, except for, of course, 0. If we take the slope and look at the change, it actually changes exponentially. And because it changes exponentially, the second derivative is also going to be exponential, and so on and so forth. Next up, we have maybe our most annoying rules because there's so much memorized. But trust me, if you just practice all of these problems, you'll get it down like muscle memory down pat. Okay, so let's start with our sine function. And so going down will be our d over dx here. So the derivative of sine is cosine x. You have to use Euler's and all that. And I mean, if you really want to, you can look up all the proofs if you don't believe me or something like that. So the derivative of cosine is negative sine. The derivative of negative sine is negative cosine, which makes sense because if you remember our constant rule, this is actually just negative 1 times sine x, which we already showed was cosine x as a derivative. And then the derivative of this, and cosine goes to negative sine, negative times negative is a positive, so it just becomes sine x. So this repeats over and over. There are other ones, though, do not repeat. So let's look at tangent x. If we take the derivative of that, we get secant squared x. Secant x, if we take the derivative of that, we get secant x tangent x. For cosecant x, we get negative cosecant x cotangent x. And for cotangent x, we get negative cosecant squared x. So if you notice a bit of a pattern here, the tan and cotangent is just what the other function squared, and all of the cos, the ones with the c's, are negatives. And then for secant or cosecant, the ones that end in c's, they also have these two functions multiplied against each other. So you can sort of bracket them off like this if it helps you to remember. Next, of course, we have our inverse trig functions. And so that includes things like the arc sine, which if we take the derivative of will get us 1 over the square root of 1 minus x squared. Arc cosine x, which goes to negative 1 over 1 minus x squared. Arc tangent x, which is the same thing as arc sine times arc cosine, so we'll get 1 over 1 plus x squared. Arc secant x, which goes to 1 over the absolute value of x times 1 minus x squared. Arc cosine x, which is the same thing but negative. And then finally arc cotangent of x, which is the negative of arc tangent. And so this may seem like a lot, but you really do need to memorize these. Like if there's anything you need to memorize in this class, it's the integral rules and this thing right here. All these, like this sine, cosine, that should be fairly easy. This you can bracket off. And this, if you need a pattern, cosecants will always be, or cosines will be the negatives of sine and secant, which are positives. S positive, C negative. And then tangent and cotangent are opposites, of course. And you can remember cotangent is weird, so it's negative, and therefore they're bigger, so they can be considered 1 plus x squared. That's at least how I remember it. Very unmathematical, but it works, And so before I go any further, let's cover our most important rule, and that is the holy grail of calculus, chain rule, which states that if your function can be written as a composite function, or f of g of x, or as y equals f of g of x, well, then the chain of this essentially means that y prime equals the derivative of the outer function times the derivative of the, and this has a multitude of uses. And so while it makes work a lot easier, it also makes it easier to justify giving you harder problems. So let's look at an example. Very easy. y equals sine 5x. And so you notice this method here only applies for sine of x. What do we do when we have a 5? So the outer here is sine x. It wraps around the function. So you can think of it sort of like a Russian nesting doll. You have the inner, and then the outer, and then outer and outer, however many there may be. So sine 5x, we take the derivative of the outside, which is cosine 5x, and we multiply it by the inside's derivative, which is 5. So 5 cosine x is the derivative. And as I alluded to with this nesting doll example, we can make this much more complex. Let's say we have cosine of sine of 5x plus 2 squared. And that's a lot of parentheses. Okay, so we just have to keep on working our way from out to in. So the derivative of cosine is negative sine, and then we just drop all this down, which I don't feel like writing with my mouse, as you can see. And then we take the derivative of this, sine 5x plus 2 squared. And so that will be multiplied here. So we'll have, and then we multiply it by the derivative of this. And the derivative of this inside part also requires chain rule. So we'll just say cosine of 5x plus 2 squared, and then multiplied by the interior's derivative, which is going to be 10x plus 2, and then the interior of that, which is 1, and then we simplify all of this and we'll get our answer. As you can see, we can make these a lot harder, so be grateful that I'm not. And now an important thing to understand is that these rules that I've listed here are not mutually exclusive. Actually, we can even see how chain rule creates some of the other rules. So let's look at power rule, for example. So we have x squared, right? And so let's try applying chain rule here. We can rewrite this function as x squared with the squared on the outside. So if we take this as the power rule, as the outside, we have 2x, and then this goes to 1. And then we multiply it by the interior's derivative, which is just 1, which is how we get 2x. Same thing for the constant rule. In a way, we can sort of see the constant rule I mentioned earlier as an extension of the product rule. Because, I mean, look at it. Let's say we have y equals 5x. This can be written as one of the functions being 5 and the other function being x. And so if we use product rule to get the derivative of 5 is 0. So 0x plus the derivative of x is 1 plus 5. And so we get 5, which is the same thing as using the power rule, where we had 0 and brought it down. And now I'm just going to list off our final remaining rules, which all have to do with logarithms, which I'll go into further depth into another video because they're kind of complex and require us to do implicit differentiation at some point. So let's say we have a function raised to an x power. And so with this function 2 to the x, if we take the derivative of this, we're going to get 2 to the x, the original function, times the natural log of 2. And so basically what we did here was use chain rule and implicit differentiation, but that's for another video because it requires a whole video to understand, because it opens up a whole another can of worms. And so basically we can generalize this to say that the derivative of any value raised to the x power, as long as it's not a variable like x, is going to be a to the x times ln of a. And so some other ones. Let's say we have ln of x. Since we're here, the derivative of ln of x is quite easy to remember. It's just 1 over x. And in fact, we can even generalize the statement further to say that for any log base a of x, we can write the derivative as 1 over x times the natural log of the base, which is a. And so for the natural log example, the base is e, ln of e is 1, so there you go. Oh, and one last thing before I forget, is that obviously the derivative can't always exist. And we'll get into that in a different video. And so there are some limitations. For example, here in this function, x can't equal 0, because then we'll have an undefined derivative. And as a caveat to that, x also must be greater than 0. And you may be wondering why. We can have 1 over negative 2, right? But no, because it also has to satisfy this inner function as well. And as you know, the ln of any number that's negative doesn't exist, because of course it's asymptotic. And this is true for a lot of our functions here. For example, here we can have x equaling plus minus 1. carries down here and here, of course. And of course, for our trigonometric functions, we can't have values that are greater or less than 1 and -1 respectively. And so that basically wraps up the video. I'm trying out a new format where I write and speak in real time, so I apologize if it's a little scatterbrained. I'm trying to work on my ability to present here. Anyways, I hope you learned something new here, and I'll see you guys in the next video.